Okay, let's look and see what you need to know for test number 2, dos. So review through chapters 5 through 7. Certainly you need to know the difference between a discrete or a continuous random variable. Why? Because I said so. No, because you need to know if you would use the discrete probability distribution or the continuous. Remember the discrete, we had the binomial, and we had the uniform. Not the uniform, scratch that. We had the discrete, we had the binomial, and we had the Poisson. For the continuous, we had the uniform and normal. All right, so the number of premium channels, what I do to know that it's discrete, it's countable, and typically it'll say number. Okay, so the number of actual channels would be discrete, countable. The time it takes to wait in line at the bank, anything you can measure, continuous. Okay, so those are kind of the key words. Anything you can measure, your weight, your height, time is on my side. Anything like that is going to be continuous. All right, so what if I asked you, does this probability distribution actually meet the requirements? Well, the first thing you want to do is look at all these probabilities and make sure they're 1 or less, right? And then you also want to make sure that all the probabilities add up to 1. So, yep, they were all certainly between 0 and 1, no negatives. And then I add all of them up, and I do get all the probabilities add to 1. All right, find the expected number of interruptions per day. Expected, did we go over that? Yeah. So expected value is the mean. For a discrete probability distribution, you find the mean by taking each x value times its probability, each x value times the probability, each x value times the rate, each x, and then you add them all up. So that is the expected, so in other words, interruptions per day, that is the expected number of interruptions per day. Like, how many times do we expect Ricky in class to interrupt me? Ha ha, hey, gotcha. All right. Find the variance. This one's a little bit harder and more drawn out. So the formula says to take each x value, so that's this first column, and subtract the mean, the 1.4. That's what we just found right here. Okay, so we had to find the mean first. Take each x value minus the mean, square it, times its particular probability. All right, so each x value minus the mean, each x value minus mean, each x value minus the mean, blah, 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 square them, multiply by each of their probabilities, and add them all up. Then how would you find the standard deviation? We know if we have the variance, we just take the square root, and that gives us the standard deviation. All right, binomial distribution. If a particular document has mistakes, it is tagged. Recent data shows the likelihood of a tagged order is 0.10 or 10%. What is the probability there are 3 tagged documents in a sample of 4? So it's either tagged or it's not tagged. That's how we know it's binomial. So what is the probability there are exactly 3? So this would be x equals 3. This is my formula for the binomial distribution in the total number of documents, 4, x, the number I'm interested in, 3, and then n minus x, my sample size minus my x value, p, the probability of success that it's tagged, raised to the number of successes, which I'm looking for, 3, times the probability it's not tagged. Well, if 10% is tagged, 90% or 1 minus 0.10 would be not tagged. If 3 out of 4 are tagged, how many are not tagged? That would be 4 minus 3, and that's where we get the 1. Remember, the factorial means 4 times 3 times 2 times 1, but I can stop at 3 factorial because I see that down here to cancel it. 4 minus 3 is 1. 1 factorial is just 1. So all I have left is 4. And then throw all that in your calculator, and you should get that answer. All right, what is the probability there are 3 or more? So 3 or more would be 3 and then also 4. Okay, the only thing kind of to note with the 4 is, remember, 4 minus 4, 0 factorial means 1. Okay, so that's 1. So you simply find 3, you find 4, and you add the 2 together to get your probability. What's the probability there are less than 3 tagged? Now, if you want to less than 3, you could actually do less than 3, which would be 0, 1, 2, and add them up, or you could do 1 minus the complement, okay, which would be more than 3, which we just found on the last question. Okay, and so we would take 1 minus that value to get our probability. All right, assume baggage is rarely lost, rarely, Poisson distribution. Suppose a random sample of 1,000 flights shows a total of 300 bags were lost. If the number of lost bags per flight allows a Poisson distribution, compute the probability of not losing any bags. So X is 0, not losing any. You got your Poisson formula right there. Remember that lambda is the mean, how many we would expect? Well, in this case, they don't give that to you. You have to compute it. So we would expect 300 out of 1,000, 0.3, raised to the probability I'm looking for, X equals, if the number of bags follow, compute of not losing any bags. So X is 0. E is E, and raised to the negative lambda, and divided by my X factorial. Throw all that in calculator, that's what you get. All right, here it says the probability makes 7 mistakes if 10,000 are checked. And so I want to look at the actual probability, X equals 7. Okay, suppose someone entering data makes a mistake with this likelihood out of 10,000. You see where the 2 comes from? All right, so in this case, I have to find the expected number. I raise to the number that I'm looking for. E, again, raised to my mean, my negative lambda, and then over my X factorial. All right, uniform. Suppose the amount of time it takes to assemble a particular item ranges from 27 to 39 minutes. And assembly are uniformly distributed. Find the mean and the standard deviation. So you got your formula sheet. You got your formula sheet. So the mean is just adding the range divided by 2. The standard deviation, subtracting the range divided by the square. Where's square root? Where'd 12 come from? Because I said so. That's formula. Okay, I can prove it if you want me to prove it, but that's the actual. You will always use the square root of 12. All right, so that is your formula. Find the probability that a given assembly will take between 30 and 35 minutes. The probability goes up top, between 30 and 35. And then the range, the 39 minus 27, goes on the bottom. And I get 0.4167. Fewer than 30 minutes. Fewer than... So I know 30, but to what? Where do I stop? Well, you stop within your range. So 30 or fewer till I hit the bottom value, my range. And then, of course, the bottom is the range of the entire distribution to get my answer. Normal distributions, men's heights are normally distributed. Z-table, you got your Z, where's my Z-table? You got your Z-table? I got my Z-table right here. You thought I didn't have it, huh? Right there it is. In fact, I got 2 of them. All right, are normally distributed with a mean of 70.1 inches and a standard deviation of 2.8. The standard doorway height is 80 inches. What proportion of men are too tall to fit through a standard doorway without bending? Well, then what I would do is I would take the 80 minus 70.1, that's the mean, divided by the standard deviation. I get 3.54, and I look in my table, and there ain't no 3.5. It's 3.49 is the largest value. Well, if you notice, that's pretty much, you've almost got to 1, okay? But I want the greater than side. They're too tall, so I take 1 minus that value, which is practically 0. I mean, if you use a computer, you'll see there are some decimal places out there, but if I round to 4 decimal places, practically 0. All right, well, what if we want to figure out what is the height that cuts off the tallest 5%? Well, 5%, how did I get that? Oh yeah, because from all the way to infinity up to that value would be 95%, 0.9500. You're looking within the table. You're not looking at the Z column. You're looking for the value closest within the table. If I look up, I find 0.9495 and 0.9505. They're the same distance, so what we do is we average the two Z values. So we take 1.64 plus 1.65, and that's where that number comes from. I want to know what the cutoff is, so I want to solve for X. That's still the same mean, still the same standard deviation, and I solve this for X to get my answer. All right, and then finally we have the binomial approximation. So in other words, if I don't want to use the binomial, I want to use the normal to approximate the binomial. What do you need? That table right there, that continuity correction, because we're making a discrete continuous. So notice if I want exactly 12, if I want exactly, then I do minus, which would be 11.5, minus 0.5, and then I do plus 0.5, so that's going to be a lower Z and upper Z. I take those two values and I look them up in my table. You got your table still there? So look them up. Don't just say, Cindy, I see what you did. No, you didn't, because you didn't look in your table. Look in your table. Pause me. Pause. Okay, we're back. You didn't pause me. Look those values up and you get this. We subtract them. Why? Because what we've done, instead of 12, we've made it an actual range of 11.5 to 12.5, the area between we subtract. All right, now you might say, but what about chapter 7? Well, we just did that in class, so review chapter 7. All right, so chapter 7, probably the only big things, were the different types of sampling. The activity we did in class would be a good thing to study. And then your project, the very last question where you had to divide by the square root of the sample size, that's a great example to study as well. So study, you better study.